Hi everyone, good morning. Thank you to Amber and the SLC6A1 community for getting us all together to share our work and continue the move forward. I'm presenting this on behalf of the UT Southwestern team that's working on SLC6A1, and a lot of the work that's being presented today is a collaborative effort. So I'm going to start off where Marie left in terms of the seizure profile, and I'm going to focus most of the time here today on the EEG data that we've been studying. So as Marie described, in terms of the qualitative EEG and the reports that are generated when a qualitative EEG is read, many of the EEGs in very young children who are under 2 could be normal. As the children grow older, we notice that the abnormalities start to increase, and the abnormalities come in many forms and varieties. And to your right, you can see the graph that shows the incidence of the different abnormalities with generalized spikes and the rhythmic delta activity, RDA, which is what we're going to focus on today, being a very significant finding. And so when we were reading these qualitative EEGs, we noticed that there was this signal of high amount of rhythmic delta activity that we were seeing in this group of patients. And as they were coming for their repeat EEGs annually for the natural history study, we noticed that this rhythmic delta activity persisted and sometimes increased as the child became older. And so that is what prompted us to pick up on the signal of rhythmic delta activity and dive a little deeper into it and see if we can extract a signal that could help with various aspects of potentially treatment going forwards. And first of all, understanding what the rhythmic delta activity means in terms of the clinical profile of the patient. So here is the qualitative EEG and a graph that kind of highlights what I just spoke about. By age 3, a lot of the EEGs became abnormal, and by age 6, majority of the EEGs were abnormal. But under the age of 2 to 3, some of the EEGs were normal. These are some examples of the qualitative EEG. So this is what we were looking at when we were analyzing the raw EEGs and generating reports. And to your right side on the top is the term OIRDA, occipital intermittent rhythmic delta activity. And what you see in the blue and red at the bottom of each panel is what signifies OIRDA. And that's basically telling us that there is a lot of delta frequency activity, meaning activity that's in the 1 to 4 hertz spectrum, and predominantly in the back of the head in the occipital region. And we also noticed that in some other patients, the rhythmic delta activity was pretty diffuse. It was not specifically in the occipital region. It would vary between patients and among each patient over the years and shift between this pattern of occipital to temporal and frontal, and overall just this increased signal of a lot of rhythmic delta activity in the 1 to 3 hertz range. So although delta falls in the category of 1 to 4 hertz, what we were seeing is the delta that we were seeing in the SLC6A1 patients was predominantly in the 2.5 to 3.5 hertz range. And we also noticed that the rhythmic delta increases with age. So just to kind of get into the delta power that we wanted to study further, it's a measure of EEG activity in the 1 to 4 hertz range. There's not that much data available in literature as to what the normal delta power is supposed to be based on the age of the patient. As we all know, as children grow older, their brain matures, and similarly the EEG matures as well. And it's normal for very young babies to have delta and theta activity. But as they grow older, this amount of delta activity reduces and is replaced by predominantly faster frequencies. And so we tried to extract some normative data and try and analyze how much delta power is normal as the child matures. And we also wanted to look at activity by region in terms of frontal versus temporal versus occipital or generalized rhythmic activity. And we wanted to look at awake versus sleep, because EEGs can change as we sleep, and the amount of delta activity naturally increases in sleep for most of us, including children. And so we wanted to parse out all of these aspects. And just to kind of refer, those two references that you have there refer to Angelman syndrome. So there's a lot of work that's been done in Angelman syndrome where a specific type of delta activity was noted, which was very high amplitude, and they were able to tease it apart further and use it as a marker for treatments. And so we kind of referred to that process and used that as our guide. So we looked at 20 patients in the natural history study who underwent 4-hour video EEGs at UT Southwestern and Children's Health. And many of these children have come back for their annual EEGs. So we have up to 4 EEGs in some patients done every year. And initially, we used EEG Lab, which is an open source software using MATLAB to analyze the data. And as the signals started to emerge in terms of the importance of the rhythmic delta activity, we decided to also use PERSIST, which is, we also decided to use PERSIST, which is a software that's embedded into many of our EEG analysis softwares. And so since this is embedded into our EEG software and clinically available at many centers, we thought that using EEG Lab first and then comparing it to the data from commercially available software such as PERSIST might then allow for extrapolation to many other centers and make it a more clinically viable tool. And several of these statistical techniques were used to analyze. So a lot of this work, especially with the EEG Lab analysis, was done by Hamza Dashi, who's in the picture there. He's currently a first-year medical student at Case Western, and he's doing his MD PhD there. So the picture that you're looking at is the image that's generated through EEG Lab. And basically, we looked predominantly at the delta frequency activity. In the x-axis, you have the frequencies, and you have the y-axis showing you the power of delta activity in microvolt square per hertz. And each of those colored lines represents a channel. And the black vertical line that you see there is trying to show us the 3 hertz signal. And the minimum 3 hertz signal in this specific patient in one of the channels was around 12, and the maximum was 20. So as you can see, the delta power can vary depending on what part of the brain we're looking at. And then we also use PERSIST, which is the commercially available software, and PERSIST generates this FFT spectrogram that you can see in the colored bar on your right. And we asked PERSIST to only export data in the 1 to 3 hertz range. And we then averaged this out and converted it to logarithmic scale, so we could then compare it directly to EEG Lab. So here's the first image. The next couple of slides are refer to the data obtained through EEG Lab analysis. And here is the first picture. And basically, what we found was that delta power above 18 might be a differentiating factor between patients and controls. So we used age-matched controls. So in blue, you have controls who are about the same age as each patient, and in red, you have the patient data. And as you can see, the red bars, especially in the left side of your, put this down, especially to the left side, shows a big deviance when compared to controls. And the areas where they were closer together, where the red and blues were closer together, were more the younger children. So the 5 of the youngest patients did not have a significantly different delta power when compared to the controls. But as the children were older and we compared them to age-matched controls, there was a big difference in delta power. Then we wanted to look at what is this relationship between delta power and age. We know that delta power is supposed to decrease with age, what happens to SLC6A1 patients as they get older. And here it became quite clear that in the blue line, you can see that in controls, the delta power goes down with age. Initially, it is pretty high. Some of them are even above 18, which is the cutoff we initially chose. But as they get older, and 13-year-old has pretty low delta power. And the control delta power decreases every year, whereas the delta power in our patients increased every year, and this was significant. Some machine learning technology was used to kind of use the age and delta power measures to tell us what is that marker that will differentiate patients from controls, and it had a pretty high sensitivity and specificity. And then we wanted to look at the correlation between EEG Lab and PERSIST, because EEG Lab is a software that we could set the settings and have a closer control over the data that's entered and the data that's analyzed, whereas PERSIST has proprietary software, and we are not completely aware of the technology that's used to produce these results. So we wanted to see how reproducible is the data when we compared to EEG Lab, which is the open source software, versus PERSIST, and it was pretty close. I will say that, as you can see on the right side, especially with PERSIST, we saw that the delta power tended to be higher in the control patients compared to EEG Lab, but in general, it was a pretty close, nearly one-to-one correlation, telling us that PERSIST is potentially a tool that could be used in the future and could be, become more clinically viable, since it is available in many centers, and it's generated automatically through running it through the PERSIST software, and does not take as much work from a person to analyze it. So that was why we tried to do that. So the next issue we wanted to tackle is the state of the patient. So being awake and being asleep are very different in terms of the EEG activity that's generated by the brain, and we wanted to look at how do we account for this. And here's an example of the graph that was generated when we compared only the awake state in patients and controls, and it still held true in terms of the difference that we had. The second issue we wanted to look at is how does age play a factor in this delta power? And we then kind of looked at the youngest to oldest patients and how this deviance from or increase in delta power accounts for, is accounted for by state. This is, I know, a very kind of colorful but complex slide, but basically what we're trying to show here is that if you look at awake versus, I don't know why this keeps moving. Is anyone moving it there, or is it just automatically? Okay. Okay, next slide, please. Okay. So we wanted to look at the awake, drowsy, and asleep states of controls versus awake, drowsy, and asleep states of patients. So if you can, please, could you go back to the previous slide? Okay, so if you look at the first patient, ID 22, you can see this pretty stark difference in awake, all three states, awake, drowsy, and asleep, in the control patient versus the sleep, versus our patient. Next slide, please. Next slide, please. Okay, so here's a slide that kind of puts it all together and looks at the whole group in terms of state when you're looking at awake and asleep and controls versus our patients. The bottom orange line is awake controls, and then if we can take a minute to pay attention to the purple and green lines. So the purple line is controlled sleep, and the green line is awake patient. And you can see that the awake delta power of our patients is similar to a sleep of controls. And the other very important fact that we saw is that when you look at the red line, you can see that the delta power is increasing in sleep as the patient gets older. And if you look at the orange line, delta power is decreasing as the patient gets older. So this to us was an important finding. Next slide, please. So here is just a qualitative figure. So we looked at a time analysis of the power of all the persist channels. To your left is a control patient whose age matched to one of our patients with SLC6A1, and it shows you the kind of amount of delta power and delta activity in the patient compared to the control. Could you go back, please? And so the green is awake, blue is drowsy, and red is sleep. So not only is the sleep delta power increased, but the drowsy has a very high peak of delta activity, and the awake delta activity is also significantly higher in this specific patient. Next slide, please. So then we wanted to see if we can get a signal. Is there a number that we can extract out of all of this that will kind of set the stage for next steps? And so we used the delta power of 19, and as you can see, the sensitivity is high, but the specificity is not that great. So a lot of controls could also have that amount of delta power if you account for lots of other factors. And if you take a very much higher delta power of 21.5, you can see the specificity is high, but the sensitivity drops. So this is still a work in progress, and we'll keep you updated. Next slide, please. And so then we wanted to see, is there a specific threshold? Is there a number that we can say that if a patient or a person crosses is a signal that tells us or differentiates things, whether it's between patient and control or in terms of severity going forwards. And as you can see, the sensitivity and specificity are higher, so this is in all states to your left and awake only to your right. Next slide, please. And the third aspect we looked at is the frequency, the number of times this rhythmic delta activity power exceeds a certain number, and we picked 860 because that was the signal we were seeing in all states, and 86 in the awake-only states. Next slide, please. So this is work in progress. We're trying to see if there is a numeric marker that kind of gives us the way forward, defines a path for analyzing various aspects of the clinical severity, and potentially serve as a marker. Next slide, please. So just to summarize, we think delta power can be quantified using both open source and proprietary software, and there's a pretty close correlation. We have found that delta power is significantly elevated in SLC6A1 children compared to healthy controls. And this average number, which we think is a number that we can follow forwards and do larger scale analysis, is maybe 21.6. And different methods can be used to capture differences to controls using PERSIST. Delta power, the third aspect we found was that delta power increases with age in SLC6A1, contrary to decrease in healthy controls. And the question is, does this contribute to the regression that's noticed in some patients? And how does this correlate with epilepsy severity and cognition? So lots of questions and lots of answers that we want to answer. And is this a potential biomarker for therapeutic studies in the future? So many limitations, small sample size, and although we tried to have an age-matched control, many times it was only one patient at that age, and so to extrapolate it will take, I think, more patients. The algorithms between EEG lab and PERSIST differ. We don't have the full details of the PERSIST algorithm as it's proprietary. We also still have a lot of work to do to account for age and maturation, and also the awake and sleep states and how this contributes to the delta power changes. And we haven't even looked at the effects of anti-seizure medications, severity of epilepsy, or genotype, which are the next steps. Next slide, please. So our next steps are to analyze the revisits. So we want to look at the longitudinal trends, because most of what I showed you today was single point data. We want to find and verify correlations between delta power and clinical features. When we looked at just one specific type of seizure, the atonic seizures, which are often disabling and result in injuries, there was a suggestion that there might be a correlation, but we want to study that further. And we want to see if there's a correlation with severity, both in terms of epilepsy, cognition, behavior, sleep, and other aspects that Marie discussed, and reanalyze data with age and medication-matched controls. Thank you.